let's solve some more problems from the chapter stress and strain. Okay, in this problem it says that in the engineering stress strain curve for mild steel, the UTS refers to, okay, so the engineering stress strain curve for mild steel, that is for ductile material, the UTS refers to the maximum stress. Okay, next question. The Poisson's ratio for a perfectly incompressible linear elastic material is, okay, you actually learn this value while you are studying the theory, that is 0.5, but let me prove how this value comes. So let us consider a cube on which in x phase, in x direction there is a stress P1, in y direction there is a stress P2, and in z direction there is a tensile stress P3. So strain in x direction will be written as P1 by E minus the lateral strains due to stress P2 and stress P3. So minus mu P2 by E minus mu P3 by E. Similarly, strain in y direction will be P2 by E minus the lateral strains by the stresses P1 and P3. So minus mu P1 by E minus mu P3 by E, and strain in Z direction will be P3 by E minus mu P1 by E minus mu P2 by E. Okay, so let's find the volumetric strain, which is equal to epsilon x plus epsilon y plus epsilon z, and which is equal to P1 by E plus P2 by E plus P3 by E minus 2 mu, taking this value common, P2 by E plus P3 by E. Okay, so this comes out to be P1 plus P2 plus P3 into 1 minus 2 mu. This is volumetric strain. Okay, now they have said that for a perfectly incompressible linear elastic material, incompressible, so that means volumetric strain has to be 0. For volumetric strain to be 0, this can't be 0, so the only term that has to be 0 is 1 minus 2 mu. So 1 minus 2 mu is equal to 0, mu is equal to 0.5. Okay, so that is how you actually get this value, 0.5. Okay, next question. A rectangular region in a solid is in a state of plane strain. Okay, the xy coordinates of the corners of the undeformed rectangle are given as, okay, so P is 0 0, this is Q is 4 0, okay, and R is 4 3 and S is 0 3. Okay, so this is 0 comma 3 and this is the rectangle 0 comma 0, this is 4 comma 3. The rectangle is subjected to uniform strains and the values are given. The deformed length of the elongated diagonal up to 3 decimal places is, okay, so you have to actually find the elongated length of the diagonal. So its shape, when the rectangle is subjected to uniform strains, its shape will be somewhat like this. Okay, yeah, and this will be the diagonal. Okay, now let this be angle theta. Okay, because if we find the strain on this diagonal, we can actually calculate the deformed length, because the strain on the diagonal will be equal to the change in the length of the diagonal upon the original length of the diagonal. So from this equation we can find the deformed length of the diagonal, and hence the elongation in diagonal, and hence the deformed length of the elongated diagonal. So theta, let this be theta, and theta is positive when it is taken in clockwise direction, from the positive x phase. This is the sign convention, from positive x phase. Okay, so theta is positive. Now can I find out what theta is, what the value of theta is? Tan theta is, this is 4 and this is 3, so 4 by 3. So that implies if you take tan inverse theta will be it comes out to be 53.13 degrees. So if I find the strain at an angle of 53.13 degree, it actually gives me the strain on this diagonal, and strain is equal to the change in length upon original length. So we can find the change in the length of the diagonal, and from this value I will be able to find the final deformed length of the diagonal. Okay, so theta is 53.13 degrees. Now we have our formula, that is strain at an angle theta is equal to Ex plus Ey by 2 plus Ex minus epsilon x minus epsilon y by 2, that is strain in x direction, this is strain in y direction, cos 2 theta plus gamma xy by 2 sin 2 theta. Gamma is shear strain on xy plane, gamma xy by 2 sin 2 theta. Okay, so now we have all the values, strain in x direction, strain in y direction, and the shear strain on xy plane is given. Put the values, it will be 0.001 plus 0.002 upon 2 plus 0.001 minus 0.002 upon 2 cos 2 theta, that is cos of 106.26 degrees, plus gamma xy, that is 0.003 upon 2 sine 106.26 degrees. Okay, so when you solve it, this value will be 1.5 into 10 to the minus 3. This total value will be 1.4 into 10 to the minus 4, and this value will be 1.44 into 10 to the minus 3. Okay, so in all, the strain on this angle theta will be 3.08 into 10 to the minus 3, and I have told you, and also we know, that strain is equal to change in length upon original length. So let this be delta L upon original length. What is the original length of this diagonal? If this is 4, this is 3, this is 5 by Pythagoras theorem. So that implies delta L is 15.4 into 10 to the minus 3 units. Okay, now it has been asked that you have to find the deformed length. Okay, so the deformed length, that is final length, will be initial length plus delta L. Okay, so the initial length is 5 units plus the deformation is 15.4 into 10 to the minus 3 units. Okay, so the new length is actually 5.054 units. This is the deformed length of the diagonal. Okay, so this was a good question. Let's move on to the next question. A horizontal bar fixed at one end, x is equal to 0, has a length of 1 meter and cross-sectional area of 100 mm square. Length of 1 meter and cross-sectional area is 100 mm square, that is 100 into 10 raised to the power minus 6 meter square. Its elastic modulus varies along its length and is given by this relation, and this elastic modulus is in GPa. Okay, take care of the units, where x is the length coordinate along the axis of the bar in meters. An axial tensile load of 10 kilonewton is applied at the free end where x is equal to 1 meter. The axial displacement of the free end is, okay, let this be a bar, horizontal bar, okay, and at a distance x, okay, from the fixed end, not from the free end, from the fixed end, because here x is equal to 0 and here x is equal to 1 meter. So at a distance x from the fixed end, let there be an element of length dx. Okay, now the elongation, I mean there is a load also, P is equal to 10 kilonewton. Okay, axial tensile load. So the elongation of this dx element due to this force P can be written as del x is equal to P dx by AE. Okay, how, I mean when an axial tensile load is acting on a horizontal bar, how the total elongation of the bar is written, it is written by delta is equal to PL by AE. So here the elongation of dx is represented by delta x and length of the element is dx here. Okay, rest of the terms are same. Now integrated from the limits, which is 0 to delta and 0 to 1 meter. Okay, now delta is equal to 0 to 1 and P is 10 kilonewton, 10 into 10 to the power 3. This is dx. A is 100 into 10 to the power minus 6 meter square, and E is the relation is given, that is 100 into e raised to the power minus x GPA. So you have to convert it in Pascal. That implies you have to multiply it with 10 to the power 9. Solving it, I guess this will be 10 to the power minus 3 integration from 0 to 1 e raised to the power x dx. So that implies delta is equal to 10 to the power minus 3 e raised to the power x 0 to 1. This will give me delta is equal to 1.718 mm. Okay, this is in meters, but as we have 10 to the power minus 3 here, so I can directly write it in mm. So the axial displacement of the free end will be 1.718 mm. Okay, so next question. This question is directly based on the formula that we study. A point mass of 100 kilogram is dropped onto a massless elastic bar. Cross-sectional area is 100 mm square, that is 100 into 10 to the power minus 6 meter square. I like to work in SI units so that there is a less chance of making silly mistakes. Length is 1 meter, Young's modulus is 100 GPa, that implies 100 into 10 to the power 9 Pascal, from a height h of 10 mm, that is 0.01 meters. If g is 10 meter per second square, the maximum compression of the elastic bar is. Okay, so this question is directly based on the formula that the deformation in this bar by this impact load is equal to delta impact is equal to delta static into impact factor. Okay, what is delta static? Delta static is PL by AE, which states that here P is 100 into 10 Newton. Okay, 100 kg into 10 is the value of G given. So I mean P is equal to mg here, and L is 1 meter, the length of the elastic bar. Area of the bar is 100 into 10 to the power minus 6 meter square, and E is 100 into 10 raised to the power 9 Pascal. Okay, so when you solve this delta static, it will be equal to 10 raised to the power minus 4 meter. Delta static is, delta static means that this 100 kilogram mass is not dropped from the height, but instead it is gradually applied on this bar. Okay, and delta impact is found by this relation, that is delta static into impact factor, where impact factor is equal to 1 plus 2h by delta static. This is the formula for delta static. Sorry, impact factor. So impact factor is equal to 1 plus under root 1 plus 2h is the height from which this mass has been dropped, which is 0.01 meter, and the delta static I have found out, that is 10 raised to the minus 4 meter. Solve it, you will get impact factor is equal to 15.177. Okay, now I have impact factor and I have delta static. Multiply both of them and you will get delta impact. The value of the delta impact will be 10 to the minus 4 into 15.177 meters. Converting it to mm, because I have to fill the answer in mm, the value will be 1.5177 mm. So the answer will be 1.5177. The maximum compression of the elastic bar is. Okay. Next question. A rod of length 20 mm is stretched to make a rod of length 40 mm. Okay, so the initial length of rod is 20 mm and the final, not the final length actually, and it is stretched to make a rod of length 40 mm. Subsequently, it is compressed to make a rod of final length 10 mm. Now this is the final length. Consider the longitudinal tensile strain as positive and compressive strain as negative. The total true longitudinal strain the rod is. Okay, the sign convention is also given. So engineering strain is basically change in length upon the original length. Change in length is, the final length is 10 mm, not 40 mm. Okay, and the initial length is 20 mm. So the engineering strain will be minus 10 upon 20, that is minus 0.5. Okay, minus sign represents that the length is decreasing. True strain is ln 1 plus engineering strain, and which is equal to ln 1 minus 0.5, that is 0.5. ln 0.5, the value of ln 0.5 is minus 0.693. So this is our answer, that is option B. Let's move on to the next question. A biometallic cylindrical bar of cross-sectional area 1 meter square is made by bounding steel whose Young's modulus is 210 gigapascal and aluminium whose Young's modulus is 70 gigapascal as shown in the figure. To maintain tensile axial strain of magnitude 10 raised to the power minus 6 in steel bar and compressive axial strain of magnitude again 10 raised to the power minus 6 in aluminium bar, the magnitude of the required force P in kilonewton along the indicated direction is. Okay, so the magnitude of strain in both the bars is same, and if I apply a force P like they have applied in this given figure, there will be reactions on the steel bar and aluminium bar. So let's see. This is the steel bar, this is the applied force P, this is the aluminium bar. So let the reactions on the steel bar and the aluminium bar be denoted by PS and PAL. Okay, and the reactions are in the opposite direction, and the reactions PS and PAL are in the opposite directions to that of the net force P that has been applied on the intersection of the bars. Okay, so sigma fx is equal to 0, and this gives us PS plus PAL is equal to P. Okay, this is our first equation. Now they have given us the strain in steel bar is 10 to the minus 6, and the strain in aluminum bar, the magnitude of the strain in aluminum bar is also 10 to the minus 6. So PS by AE is actually 10 to the minus 6, because PL by AE is delta. If I take L below delta, this will give me strain. So PS by AE is equal to 10 raised to the power minus 6. That is tensile axial strain in the steel bar. So from this I can find out PS, because everything is given to me. 10 to the power minus 6 into area is 1 meter square into Young's modulus of steel, which is 210 into 10 to the power 9 Pascal. So this is 210 kilonewton. Okay. And similarly, PAL upon AE is equal to 10 raised to the minus 6 again. So I can find out PAL, which is equal to 10 raised to the minus 6 into area is 1 meter square into the Young's modulus of aluminium, which is 70 gigapascal, that is 70 into 10 to the power 9. So this gives me PAL is equal to 70 kilonewton. Great. Now from equation number 1, PS plus PAL is equal to P. That implies the magnitude of the required force P is 210 plus 70 kilonewton, that is 280 kilonewton. This is P. Okay. Thank you.